Right, as ever so often I have to start this lecture with correcting a mistake from last time. It's not a big mistake this time, but nonetheless I want to correct it. I talked about this chirp signal, and I also show you a draft of this I had produced. So this was for an in-spiraling binary of 2 point masses. So I've told you that the signal would look something like that. And it then becomes infinite and it reaches a limit. Okay, the qualitative feature is correct, but the quantitative equation, as in the way I've written it, was not correct. I've written that it is of the form h of t is a constant, h naught. I leave a gap here, omega t squared, and then cosine 2 omega of t times t plus a constant phase. And what I overlooked, that this quantity, which I had called h naught, is actually not a constant. It involves a factor a, which is the semi-major axis, or because we are considering this circular orbit just the radius, that it contains this squared. This, of course, also depends on t. And this, if you use Kepler's third law, then you see the whole thing is proportional to 1 over at, or what is the same, to omega over t to the power 2/3. Not to the power 2, but to the power 2/3. Okay, qualitatively this doesn't make a difference. Omega t goes to infinity. And if it goes with the power 2 or with the power 2/3, anyway, it goes to infinity. Yeah, so this was correct. But the way in which it goes to infinity is actually not quite as fast. Yeah, it goes with a lower power. So in the written version I've sent around, it's correct. But when I showed you this last time here in the lecture, I had a wrong factor in the exponents. That was one thing. And the other thing, I mentioned that we are fairly sure that the companion in the Hals-Taylor pulsar, of the Hals-Taylor pulsar is also a neutron star. And then Pavel asked me, why are we so sure? Couldn't it be, for instance, a white dwarf? Actually, I tried really hard to find a solid confirmation that it is a neutron star, and I was not able to do this. So the mass of the companion is now known very well. Yeah, it's known, I think, until 5 digits or so. So it's 1.38 something solar masses. 3/8, that's less than 1.4. 1.4 is the Chandrasekhar limit. Yeah. So as far as the mass is concerned, it could be a white dwarf, actually. But, well, I checked also recent publications where people say, well, we are fairly sure that it is a neutron star. And I couldn't find really a convincing argument why we are so sure. I guess that the reason is that if it were a white dwarf, we would see tidal deformations. Yeah? We know this system now with such a high accuracy that although the 2 stars are fairly far apart in comparison to their radii, that probably tidal deformations of the white dwarf would be visible if it were a white dwarf. That's what I guess. But I couldn't find a real convincing confirmation of this. So what you find in the literature statement, something like, we are fairly sure that it is a neutron star, but at least I was not able to find a rigorous confirmation of this. Okay, so this was the 2 afterthoughts about what I did last time. And now let's continue with the calculation we interrupted last time. So I'm now talking about gravitational wave detectors. And I began with these somewhat outdated, but nonetheless interesting type of detectors, which are called resonant bar detectors. Yeah, these Weber cylinders, as they are also called. And as a very simple model of a Weber cylinder, I consider just 2 masses of a string connected by a spring. So the idea is that the geometry is like that. We have 3 spatial axes, x1, x2, and perpendicular to this x3. And the gravitational wave is supposed to come in the direction of x3. Then this here, this angle is the angle theta. So of course, we cannot expect that that our detector, if I'm allowed to call this a detector, that this is aligned with a gravitational wave in a perfect way. So in general, there will be a certain angle phi here and a certain angle theta there. and we are calculating the way, the kind of oscillation which would be excited in the spring by this incoming gravitational wave. So, okay, let me write another picture, because otherwise you couldn't read it. We had introduced the following notation. We had called the equilibrium elongation SL. And then if the thing is oscillating, the elongation will differ from SL by something which I called psi L of t. So psi L is the change from the equilibrium elongation. And the goal was to derive a differential equation for this psi L. And we linearized with respect to psi L and its derivatives. And what we got, this was the last equation which was on the board, was an oscillator equation for this psi L. Let me write it again. No, it's not on this page. Oops. Where we are. Here we are. So it's an oscillator equation, a damping term, gamma over m. Gamma is a damping constant. And then the restoring force, k over m, psi of t. K is a spring constant, right? We linearize the system, so we assume that we have a linear relation between elongation and force. And on the right-hand side, well, this time I write it a little bit different from what I've written last time. Allow me to write it in this form, s omega squared. Omega is a frequency of the incoming gravitational wave, cosine 2 phi. The angle phi is in the picture. Sine squared theta, the angle theta is also in the picture. And let me write this in the form real part of a plus e to the minus, yes, minus I omega t. I've written it last time a little bit different, in a little bit different way, because I had calculated this real part, assuming that a plus is real. Actually, this is possible, but I realized later that it's not convenient for what I'm planning to do. So in the following, I will work with this expression. But let me quickly point out that it is actually the same as what I've written last time. So this expression, real part, a plus is the amplitude of the incoming gravitational wave. And then I have this phase factor. Well, this is in general a complex number. Yeah, the amplitude. We have here a plus mode. We assume that we have only a plus mode. You can do it for a superposition of plus mode and cross mode. Not much more complicated, but for the sake of simplicity, let us assume we have only a plus mode. So this would be a modulus times a phase, e to the I phi, e to the minus I omega t. And if you now write this, write the real part out, you get a plus modulus. This is real. And the real part of this is just the cosine. Cosine of phi minus omega t, or as the cosine of phi is the same as the cosine of minus phi, I can also write it in this way. And I continue writing this as cosine as omega t minus t1, where I've introduced just a time shift, a shift on the time axis, where t1 is what? T1 is phi over omega, right? So if I now shift the 0 on my time axis, I have just cosine omega t. Yeah? I can choose a 0 on my time axis wherever I like, so I can make this term equal to t, and then I have just the modulus of a plus times the cosine of omega t. So if I would like to write it out in this way, I could do it. I could also do it with a minus sign. That's maybe a little bit confusing, but I could write the same thing also if I like to, in the way this is minus a plus e to the I phi e to the minus I omega t, and then I have to compensate for this minus sign. Minus 1 is e to the I pi, right? So I can multiply this with e to the I pi. Then this is minus 1. And together with this minus sign, it gives again a plus. It gives the same thing. And if I use this expression, then I get minus a plus cosine of omega t minus phi minus pi. And I can write this, if I like to, in the form minus a plus cosine omega t minus a different time shift t2, where now t2 is phi plus pi over omega. So you shouldn't be confused if you see this equation sometimes with a minus sign and sometimes without the minus sign. Yeah? It is just a matter of where you put the 0 of your time axis. So this is just a matter of convention. But actually, after I had done the calculation in this, with this expression, I realized that it's much more convenient for what I'm planning to do just to leave it in this way. So we can now forget about this. We just leave it in this way as it actually would have come out originally. And yeah, let's solve this differential equation. So I solve it in this way now. So this is obviously a linear but inhomogeneous differential equation. Yeah? Linear second order differential equation for psi of t. And I hope everybody, with constant coefficients. So it's very simple. So I think everybody knows what to do. The general solution is the general solution to the homogeneous equation plus one particular integral to the inhomogeneous equation. So the general solution to the homogeneous equation so what do you do if you have a linear differential equation with constant coefficient? Then there's an algorithm which always works. You choose an exponential ansatz. It always works. Yeah? So you choose exponential ansatz. Psi of t is, there's a constant, let's call it c. It will be complex in general, of course. E to the I, no, not to the I, e to the kappa t. And kappa, of course, in general will also be complex. Then I have, if I feed this ansatz into the homogeneous equation with a 0 on the right-hand side. Yeah? Okay, let me write it down again so that everybody knows what I'm doing. Plus gamma over m d psi dt plus k over m psi of t is 0. That's the equation we want to solve at the moment. Plug this ansatz in. Then we see that that we get, do I want to call it kappa? Yes. Oops. Yes. Okay, so whenever I take a derivative, the exponential function reproduces itself. So I get this factor in front of everything. The second, first derivative gives the factor kappa. Second derivative gives the factor kappa squared. Then plus gamma over m. First derivative gives the factor kappa. And here I just, I don't have to take any derivative. So this is just k over m. Okay, our constants, of course, is supposed not to be 0. Otherwise, we have the 0 solution. We are not interested in this. And the exponential function also has no zeros. So we have a quadratic equation for kappa, which can be easily solved. So kappa, there are two solutions, kappa 1 and kappa 2. Quadratic equation minus gamma half divided by m plus minus root gamma squared over 4m squared minus kappa m. Now you see there are two cases. Either what I have under the square root is positive, or it is negative, or it is 0. That's a limiting case. If it is positive, then both solutions are real. Yeah, if this number under the square root is positive, then both solutions, kappa 1 and kappa 2, are real. This means I have something which is exponentially growing and another solution which is exponentially decaying. I have nothing which is oscillating. But I want to have my spring oscillating. So for oscillating solution, we need what is called, we assume, under critical damping. So the damping, the gamma should not be too big. Under critical damping, which means that this is negative. Gamma squared over 4m squared is smaller than k over m. Yeah? Then I have a negative number under the square root. This means, oh, let me write it in this way. So this here is, no, the other thing. This is positive. Okay, let me write it clearly. So I assume that minus gamma squared over 4m squared plus k over m is negative. So I assume this. No, it's positive. It's positive. Sorry. Oh, my goodness. It's positive. If it's positive, I can write it as the square of a real number. And I call this omega naught. Yeah? Omega naught is real now, by assumption. And then I have my kappa 1, 2 is what? It's minus gamma over 2m. Plus minus. And here I pull a minus sign out of the bracket. Then, because it's under the root, it becomes an I. And under the root, I have omega squared, so I get plus minus I omega naught. Okay? So then I have oscillating solutions. So the general solution to the homogeneous equation, in this case, if you assume under critical damping, is then a superposition of the two solutions, one with kappa 1, one with kappa 2. So it is psi of t is C1 e to the kappa 1t plus C2 e to the kappa 2t. And what is this? Oops, that's C1 e to the kappa 1 is e to the minus gamma 2m plus I omega naught plus C2 e to the minus gamma over 2m minus I omega naught. And I can, the exponential factor with the gamma right in front of everything. There's a t missing. Sorry. Oops. Here's a t and here's a t. Oops. T C1 e to the I omega naught t plus C2 e to the minus I omega naught t. So what is this? This is an oscillatory solution. Yeah, it oscillates with this frequency omega, which is given by the spring constant modified by the damping. And then I have this factor in front of everything. Of course, I assume that gamma is positive. I have a damping. Not something which increases the amplitude. Yeah? So the gamma must be positive, then I get a damping. So if I write this on the right-hand side, then I have minus gamma over m times the velocity. So the velocity is, it's counteracting against the velocity. So this is decreasing. Yeah? So if I wait long enough, whatever the initial conditions are, which determine the C1 and the C2, whatever the initial conditions are, the solution dies down because of this factor. Yeah, it goes down exponentially with this factor in front of this. So we see if I wait sufficiently long, then the character of the solution is dominated by the particular integral. Yeah? The solution to the homogeneous equation dies down in the course of time if I have under critical damping. So we need one solution to the inhomogeneous equation, one particular integral, and this will determine the behavior of the solution. So one solution, one particular solution to inhomogeneous equation. Well, I solve this well. I have a driving force. It's there in the top line. I have the equation I want to solve now. I want to find one particular solution, psi of t, of the equation in the top line. You see on the right-hand side, I have an exponential time dependence. So if I want to solve this equation, it's very natural to assume that the solution is also depending on time in this, with respect to this frequency. So I assume that psi of t is a real part with some amplitude a. I called it A. I realized later that I had used A before for the semi-major axis, but I think there's no confusion, no danger of confusion here. Yeah. So now at the moment we have no semi-major axis in this game. So this is just the amplitude of my solution, e to the minus I omega t. Yeah. So I plug this into the differential equation. Then I get the second derivative of the right-hand side. So we have to solve. Have to satisfy the following equation. Real part. Well, everything contains e to the minus I omega t. And then let's see what we get. So I get the second derivative of psi. Second derivative of psi gives a times one derivative gives minus I omega. Second derivative gives minus times minus is plus. I times I is minus omega squared. Okay. Then first derivative plus gamma over m. Gamma over m, first derivative gives minus I omega. Minus I omega and the factor a. And plus km psi. A. E to the minus I is in front of everything. So that's the left-hand side of this differential equation. And the right-hand side I copy. So omega squared over half. Cosine 2 phi. Sine squared theta. Real part of a plus e to the minus I omega t. Okay? So we see everything contains a factor e to the minus I omega t. So I take everything to the left-hand side. And then I have what? All these terms contain an a. So I have a times minus omega squared minus I gamma over m omega plus k over m. And if I take this to the other side, I get a plus. Plus is omega squared half cosine 2 phi sine squared theta a plus. Oops. Round bracket and curly bracket is 0. Oops. Okay, so where's the time dependence? It's only in this term. So I see this term oscillates, and it should be 0 for all time. So the only way in which this could be is that this round bracket is 0, right? Otherwise, this cannot be identically 0. Well, you could also see it in this way. If you write it out, this real part, then you get a superposition of a sine term and a cosine term. Yeah, and the sine function and the cosine function are linearly independent. Yeah, so if you have a linear combination of a sine function and a cosine function, and the whole thing should be 0, then the two coefficients must be 0. Otherwise, it doesn't work. Yeah? So we conclude that this round bracket here, this round bracket is 0. So this implies that this here is 0. This means that a, okay, let me write it slowly, minus omega squared minus I gamma m omega plus k over m plus s omega squared half cosine 2 phi sine squared theta a plus is 0. That's a complex number. Yeah, a plus is in general complex, and here I have an I. So a will also be a complex number, of course. Yeah? The amplitude will in general be complex. So I can solve for a now. So this is s omega squared half cosine 2 phi sine squared theta a plus. And because I have to take this to the other side, I now get the other sign. So I get it with, I have to multiply the square bracket with a -1. So this is real. Let me begin with this real number omega squared. This is also real, minus km. And then I have the imaginary part, plus I gamma over m omega. So this is the amplitude, which is excited in my, my detector, my gravitational wave detector, by the gravitational wave. And we see, well, obviously it's proportional to A plus. Yeah? So if the incoming gravitational wave had a big amplitude, then of course the oscillation will have a big amplitude, that's clear. It's proportional to, well, it's not quite obvious what the denominator is doing. I will discuss this in a minute. But I have proportionality also to omega squared. And interesting is the dependence on the angles. So you see if sine theta is 0, then the amplitude is 0. Sine theta equals 0 means that, here's a picture, means that my detector is oriented in this way. Yeah, the gravitational wave is coming from the bottom. And sine theta equals 0 means that my spring is oriented in the longitudinal way. Well, we know that gravitational waves are transverse, so they don't produce an excitation in the longitudinal direction. Yeah. So if I want to see a signal, then I have to orient my detector in a way that it has at least a transverse component. Yeah. The optimal way is, of course, if sine theta is 1. This means if the spring is orthogonal to the incoming direction of the wave. That's the optimal thing. Yeah? So that's the orientation of my spring. That's the direction in which my wave travels. That's the optimal situation. And I also have a dependence on phi. So you see also if cosine of 2 phi is 0, the signal is there's no signal. Well, what is this? What does this mean? Cosine phi equal to 0 means phi is 45 degrees, or 45 plus pi. This means I have a plus mode, so the eigendirections of the gravitational waves are vertical and horizontal in this coordinate system. So if my spring is under 45 degrees, then also I have a signal. I don't have a signal. Yeah. So I must have, the optimal thing is that it is transverse to the incoming gravitational wave and oriented in one of the eigendirections, yeah? Either horizontal or vertical. Then I get the maximum out of the signal. And now let's discuss the dependence on the frequency. It's a little bit more complicated because of the denominator. So let me write the modulus of A. A is a complex number. Yeah, the amplitude is complex. So the modulus here in the numerator, I have only the A plus, which could be complex. So this is S omega squared half cosine 2 phi sine squared theta A plus modulus. And in the denominator, I have a complex number. What's the modulus of a complex number? It's the square root of the real part squared plus the imaginary part squared. Yeah? So it's the square root of real part squared, omega squared minus km squared, plus imaginary part squared, gamma squared over m squared, omega squared. Did I forget a factor of 2 somewhere? Let me check. I have a weak remembrance that the gamma comes with a factor 1/2. No, it's correct. No, it's correct. It's correct. The 1/2 or the 1/4 comes later. Namely, if I plot this, what one usually plots is not the A, the amplitude, but rather the A over S. Yeah, S is the elongation in the equilibrium situation, and then the psi is a change of this, and A is the amplitude of the psi. So this is the relative change in distance from the origin. Yeah, the relative change. The change in the distance divided by the distance in the equilibrium state, and that's what one calls the strain. Yeah, it's a dimensionless number. A has a dimension of a length, S has a dimension of a length. So the strain is a dimensionless number, and it plots this over omega. Okay, that's an easy exercise. That's what you learn in high school. How to you have an omega square in the numerator, and here's your omega squares in the denominator. So you have to discuss where minima or possibly maxima occur, and you see that you have only one maximum at a frequency which is suggestively called omega resonance, and the curve looks like that. Reaches the maximum, but it's not perfectly symmetric. Yeah, it's not because of the omega squared in the numerator. This is the function looks like for gamma bigger than 0. You may consider as a limiting case, and the omega resonance, you can easily calculate this. Yeah, I think I don't have to do this on the board. Yeah, take the derivative of this with respect to omega, set it equal to 0, then you find where the maximum is. And the omega resonance is actually at what? Omega resonance is at k over m divided by root k over m minus gamma squared over 4m squared. Here comes the 4. And you can consider as a limiting case the case that gamma is equal to 0, no damping. So let's again plot the strain, which is A dot over S. You have an omega S. In this case, it is just a root of k over m. Yeah, if gamma is equal to 0, well, you can see what happens. If gamma is equal to 0, then this term is not there, and then this term in the denominator becomes 0 if omega is root k over m. And there you have a singularity. Yeah? So the amplitude goes up, and it really goes to infinity. Yeah? So that's what we call the resonance catastrophe. You know this from oscillating systems. Where the most famous example is this, what was the name of this bridge in the United States? Tacoma Narrow Bridge or something like that. Have you seen the movie? It was in the 1940s. I'm sorry?
I think there's a car left, and I think there's a dog inside it.
A dog? Really? Oh, I didn't know this. I'm fairly sure that there are no humans were harmed, but I didn't know about this poor dog. So anyway, what happened was the following: that it's a suspension bridge in the United States, I think in the state of Washington, over a bay, yeah, which connects the mainland with a peninsula. And it looks quite similar to the Golden Gate Bridge, actually. It's a suspension bridge with this, of this typical style. And there was a strong wind one day in the 1940s. And unluckily enough, a resonance frequency of the bridge was excited by this incoming wind, and it excited a torsion wave in this bridge, where the amplitude became so big that actually the bridge was destroyed. So there's a movie; it's quite impressive, and apparently some of you have seen this. So something similar could happen here. Yeah, if the damping is, well, we never reach gamma equal to 0, but we could assume a fairly small damping, then it becomes, the amplitude could become very big. And then, well, actually this looks quite good, right? We could detect gravitational waves with this simple system. It would have oscillations with a high amplitude. Well, actually, the amplitude which can be reached, which means the gamma which can be reached, is not so good that we really produce high amplitudes. So for mechanical systems, for oscillating mechanical systems, the gamma cannot be very close to 0. For oscillating mechanical systems, we have, well, what one usually gives is the so-called Q factor. Q stands for quality. It's proportional to 1 over gamma. So this is what's in the numerator, root km over gamma. Yeah? So gamma equals 0 would mean Q equal infinity. So this is limited by something like 10 to the 5. Yeah? So if you have a mechanical oscillating system, a big metal block or something like that, where you excite, excuse me, where you excite a resonance frequency, then you cannot manage to make this Q bigger than something like 10 to the 5. But nonetheless, you can get some considerably high amplitudes if you are close to the resonance frequency. So that's the main lesson which we learn from this little calculation. The strain falls off rather drastically if you are away from the resonance frequency. Yeah? So this type of detectors, these oscillating systems, the resonant bar detectors, they are characterized by the feature that they operate only in a very narrow band around the resonance frequency. And we can estimate this resonance frequency. Well, first of all, I should say that the real bar detectors are, of course, not just springs. They are, I've mentioned this already, the things which Joe Weber invented and then used over many, many years were big cylinders. For big cylinders, we have to modify this calculation a little bit. Let me outline this first before I give you numbers. So maybe I should leave the picture. So this is a one-dimensional system. Yeah, I've chosen this because the calculation is simple and we can read some of the basic features quite easily. But what one really uses is a three-dimensional body, solid, an elastic solid. And then we don't have just this linear elongation psi of t. We have something more complicated. But actually, the calculation for this three-dimensional case is very similar to what I've done here. You also get kind of differential equation which has the same oscillatory behavior, the same dependence on the damping constant which is involved in the system. So I think this over-idealized case gives you a good idea of what's actually going on. So for three-dimensional solid, elastic solid body, so then the elongation psi L of t is not necessarily proportional to the s, yeah, as we have assumed here. We've assumed here that motion is only possible in this one-dimensional line. I have a coefficient here which really is direction dependent, which is usually denoted epsilon L k of t. And this epsilon Lk, so this is in this coordinates, it's a 3x3 matrix. So it's a spatial tensor, and it is called the strain tensor. So this satisfies differential equation similar to the one-dimensional case. And that's, of course, what you need if you want to evaluate observations with these Weber cylinders or similar constructions. And you can then, well, what Weber used was actually a cylinder made of aluminium. And they had typically a length of something like 1.5 meters, and a diameter of a little bit less than a meter, 60 or 70 centimeters. Yeah? So such a thing weighs about 1.5 tons. Yeah? So this is So this is, the length is approximately 1.5 meter. The radius is approximately 0.6 meter. And the mass is approximately 1.5 tons. I'll show you pictures in a minute of such a cylinder. And for this thing, you can now calculate the resonance frequency. Yeah? We can calculate the damping constants, thereby the Q factor. And as I said, for these mechanical systems like these cylinders, the best factors of Q you can reach is something like 10 to the 5. And the frequency, actually, the resonance frequency for these things is approximately 1 kilohertz. Yeah? So you get big amplitudes if you excite this with a frequency of 1 kilohertz. Now the question is, can you think of a gravitational wave that comes in with a frequency of 1 kilohertz? What kind of source could this be? You have an idea? Yeah? If you really think of a periodic source which is oscillating with this frequency, what could this be? Certainly not something like the Hals-Taylor pulsar. You remember what's the orbital period of the Hals-Taylor pulsar was?
A few hours?
The period was a few hours, 7 hours, yeah. So what is this in hertz? 2 pi over 7 hours? This is 10 to the minus 3 hertz or something like that, right? So we are 6 orders of magnitude away from this, yeah? So this is much, much too slow. A millisecond double pulsar, very good, exactly, that's what we need. Yeah. Or actually a millisecond single pulsar would already be okay if it really would emit gravitational waves. If it were perfectly spherically symmetric, then it would not emit gravitational waves. Yeah? But if it has a bump, yeah, a little mountain, a millipulsar with a little mountain, a millisecond pulsar with a little mountain, this would produce gravitational waves in this order of magnitude. And well, this is not a completely idiotic idea. People really consider the possibility that neutron stars might have small mountains. Please keep in mind, a neutron star has a radius between 10 and 20 kilometers and a solar mass. So it's incredibly dense. Yeah? So if I step on the surface of a neutron star, I would be flattened out like a postage stamp immediately, yeah? Just by gravity. But one could think of some kind, neutron star has some kind, we assume that they have some kind of crust, and in this crust there might be little bumps, little mountains. And if such a bump goes around, then it would produce a gravitational wave in this, with this frequency. Actually, I think in the next worksheet we do an example with a bumpy neutron star where we calculate the radiation emitted from this. These signals are stronger than you expect. Yeah? So actually, okay, I think that's the example we will do next time in the next worksheet. We will consider a binary system, as Pavel suggested, where one partner is a bumpy neutron star. Then the system emits gravitational waves for 2 reasons. First, we have the gravitational waves from the orbital motion. We have calculated this already. And we have the gravitational waves from the spinning motion. What would you guess? Which of the 2 has a bigger amplitude? Which would be bigger? Actually, before I've done the calculation, I would have guessed that the orbital motion has a bigger, because the masses involved are bigger. But the frequency goes with a high power. Yeah? And the frequency of the spinning motion is much bigger. And actually, the spin motion will give the stronger, well, it depends a little bit on how bumpy the thing is, yeah? So how massive this irregularity is. But for a fairly reasonable assumption on the height of the mountain, we actually will get that the bump, this rotating bump, produces a bigger gravitational wave than the orbital motion. We will do this in the next worksheet. Anyway, so this is the only kind of source for which we could expect a periodic gravitational wave signal in this frequency range. All other sources we think about, the in-spiral of 2 things orbiting each other, be it neutron stars, be it gravitational wave, be it stellar black holes, be it supermassive black holes, they have much, much less lower frequencies. So as I was just talking about the frequency. Now I come to the amplitude. I will talk about this in a minute. And we will see that for a bumpy neutron star, there's not much hope that this can actually ever be observed with such a detector. So these resonant bar detectors are actually what we can reasonably expect from them to be observed is not periodic sources, it is burst sources. Yeah? For instance, a core collapsing supernova. Yeah? If it's not perfectly spherically symmetric, if it's perfectly spherically symmetric, it wouldn't produce gravitational waves. But if it's a little bit asymmetric, then it would produce a gravitational wave. And this could have contributions also in this frequency range, which could be detected by these things. So burst sources, so in particular supernovae, are the natural candidates for what one could hope for that it would be observable with these resonant bar detectors. Supernovae in our galaxy we haven't had for a while. I might say fortunately, if it's very close it could be unpleasant. There was one 900, a little bit more than 900 years ago. Remember, this was a crab? No, I don't remember, it's good. But you have read about this. It was in 1054, I think, the Chinese observed this. It was a supernova which left the crab pulsar as a remnant. This was the last one in our galaxy. But then we had in 88, we had one in our nearest neighbor, as a Magellanic Cloud. 1988, there was a supernova in the Magellanic Cloud. In the Andromeda, also there was for quite some time no supernova. I think the last one was in the 19th century. There was one observed in Andromeda. And gamma ray burst, there was one in Andromeda fairly recently, 2014, I think. At this time, gravitational wave detectors were in operation, but they didn't see anything from this gamma ray burst in Andromeda. So if we have a supernova or a gamma ray burst sufficiently close by, this could produce a signal in such a resonant bar detector. Okay, so I was talking about the frequency. So we see the frequency is very high. That's what you should keep in mind. Later we will talk about other gravitational wave detectors. All other gravitational wave detectors are operational at lower frequencies. Yeah? So the resonant bar detectors are at the upper end of the frequency band, and they are narrow banded. Yeah, that's a bad thing. So if you are far away from the resonant frequency, or just away from the resonant frequency, need not even be very far, then you wouldn't see anything, even if it's a very nice signal. Yeah, because you must be really close to the resonance frequency. Now let's talk about the amplitude. What's the problem with the amplitude? Well, of course, there's a natural limit to changes in distance you can measure, but that's not the problem. The problem is you have to extract the signal from the noise. Yeah? The problem is not that if you have such a resonant bar detector that it doesn't move at all. Yeah? It does move. It moves for all kinds of reasons, yeah? Even if there's no gravitational waves, and that's the problem. So for instance, there's always some kind of seismic noise. Yeah? Even if you are in a region where you don't have strong earthquakes, fortunately in Germany and also in the United States, where, at least in Maryland, where Weber was doing his experiments. I think in Maryland there are no strong earthquakes. In California, of course, there are, but not in Maryland. So, but even in regions where you don't have strong earthquakes, there's also always this seismic noise, yeah? Weak earthquakes, which are very easily detectable with this kind of instruments. They are very sensitive against this. Also, the thing has a certain temperature. Weber actually worked at room temperature with his cylinders. So just because the things have a certain temperature, the atoms are moving. Yeah? And this is something which can be felt in the signal. And the main problem with the amplitude is that the amplitude must be big enough so that it comes out of the noise. Yeah? Not just that it be measurable. That's, of course, the first prerequisite, but even more than that, it must be bigger than the noise level. And how do you quantify this? So quantify the noise level. Well, you do this, you introduce something which is called the spectral density. So this is when you see a picture where the quality of or the sensitivity of a gravitational wave detector is depicted, then it's always done in terms of this spectral density. And let me briefly outline how this works. So if you assume you have your detector just under the influence of all kind of noise, but no real signal coming in, no gravitational wave coming in, here you have just all this kind of noise, then what kind of signal would you see? Well, you would see something which is random in a sense. And how could you quantify this? The usual way you do this is in terms of the autocorrelation function. So you take a signal, you measure a signal at a time t1. You see just what kind of, it's a strain. The signal is, for these gravitational wave detectors, is always a strain. Yeah? So in the one-dimensional case, it's just the amplitude divided by s. In the two-dimensional case, it's some eigenvalue or some characteristic quantity of this tensor. So you do this at a time t1. You measure the signal at a time t2, and then you do this often. So you do some kind of an ensemble average. Yeah. So, and if the system is stationary, so if there's no aging in the system or some other explicit time dependence, then this should be a function only on the difference, where t2 minus t1 is this tau. Yeah? So if I do it now and 5 hours later, or if I do it tomorrow at the same time and 5 hours later, I should get the same probability of seeing any signals. Yeah? If I have just noise, random noise. And this is what is called, this kappa is what is called the autocorrelation function of the signal, of noise signals. And now we want to know for what frequencies actually, how the signal depends on the frequency. What do you do if you want to know a dependence on the frequency? You do a Fourier expansion. Yeah? You do, and actually in this case, because we have only positive frequency, you do what is sometimes called the one-sided Fourier expansion or Fourier transform. One-sided means we take only positive frequencies. And where the Fourier transform of kappa, for some reason it's in the literature usually called SH. It's a function of omega, of the frequency. And this is defined as, Fourier transform. How was it? It was kappa of tau e to the minus I omega tau d tau, right? And there's a conventional factor. And these people who are working with signal processing, they, for some strange reason, they always use a factor 1/2. That's not what we are used to from quantum mechanics. We have a different normalization factor, but this community, they always use 1/2. And this is valid only for omega positive. And the thing is 0 for negative frequencies. Yeah? We assume that there are no, or we set up the whole mechanism in a way that we have no negative frequencies in the game. And this quantity now, this is a measure how the noise depends on the frequency. Yeah, and this is called the noise spectral density of the strain. The quantity which we are evaluating here is a strain. Yeah, these are measurements of the strain. What's the dimension of this thing? Well, the strain is dimensionless. Yeah, I emphasized this already. The strain is dimensionless. This means that this is dimensionless, this is dimensionless, this is a time. So this is a time. Yeah, SH is a time. So what one usually plots is, for some reason, not the SH, but rather the root of S of H. And this is the root of a time, which is 1 over the root of a frequency. That's this funny unit, 1 over the root of hertz. So whenever you see the sensitivity of a gravitational wave detector or also other kind of detectors plotted, you see on the vertical axis this funny unit, 1 over root of hertz. And it's the root of this quantity SH, which is plotted. And I'll show you plots of this kind in a minute for resonant bar detectors. And then later we will discuss similar pictures for the other kind of detectors. Okay. So as a measure for the sensitivity of a detector, one usually plot the root of SH, and this is in Hertz to the power -1/2. It's a somewhat unusual unit. It doesn't occur too often in physics, but here it does occur over omega, which of course is measured in Hertz. And then you see something of this sort. So here you have root SH over omega. You will get something of this kind. Yeah? What does this mean? This is a noise level. It depends on the frequency. So for some frequencies it's fairly low, for other frequencies it's higher. If now a signal comes in, if it is above this curve, then it's fine. Yeah, then it comes out of the noise and you can really observe it. But if it is lower than this, if it comes with this frequency and it is lower than this curve, then it is drowned in the noise. You cannot observe it. Yeah? And I already said what the typical sources for the noise are. So here on Earth, you always have the problem with seismic noise. And yeah, of course, if somebody walks by and hits the apparatus or so, then of course everything is shaking. This kind of noise. And yeah, what is very difficult to reduce is what comes from the temperature. Yeah. So nowadays these resonant bars are operated at very low temperature. I said already that Weber had them working on at room temperature. Now they are working at millikelvins or something like that. So then you can considerably reduce this thermal noise. Yeah, and then there are other noise sources which are contained in these diagrams. And for these, I'll show you pictures in a minute. For these resonant bar detectors, it's characteristic that this diagram has. Yeah, it comes down, so it's good, only in a very narrow band of frequencies. Yeah, and that's a major difference to the interferometric detectors. It's not so much that the noise level, just the measure is, that's also true, that this is lower, but the main disadvantage of these resonant bar detectors is that they are so narrow banded. Yeah, so the signal really has to do us a favor to come in with the right frequency. Otherwise, we wouldn't see it. Okay, now I show you. I should mention the following. So Weber. Okay, I show you the pictures first, then I say this. Okay.
Does this minimum coincide with the resonance spectrum?
Yes. Yes. So you should do the observation as closely as possible to the resonance frequency. So let's see if this works. Does it come up? Yes, it does. Okay, fine. Oops. Okay. Okay, I don't know if you can, it's a little bit darker. I think it's just in the front. Oops. It was the wrong direction. I better keep my fingers off. But I think you can see it, yeah? Can you see it? Is it okay? Okay, so this is Joe Weber. He died in 2000. He started this kind of experiments around 1960. So he did it for 40 years. And he became more and more lonesome with his experiments. So he claimed that it worked. Once he even claimed that he had found gravitational waves, but nobody believed him. And then, yeah, he became kind of bitter. So it was not, not a very, very happy story. The kind of experiment he was doing. So here you see one of his typical Weber cylinders. So as I said, the length is something like 1.50 meters. The diameter is a little bit less than a meter. And how was the deformation measured? The deformation was measured with the help of quartz crystals, which were glued to the surface. Yeah? So if now the cylinder is deformed, then these quartz crystals would also be deformed. And quartz is piezoelectric. So it transforms the deformation into a voltage. And the voltage was measured by Weber. That was the idea. And he did this experiment, as I said, for 40 years or so. He also made coincidence measurements. So he had two of these things operating in parallel. And once he said that both his detectors had detected a signal simultaneously, and he really believed up to his end that this was a gravitational wave. But everybody else said the amplitude was not big enough, so this cannot be trusted. He also had the idea, that's a really funny idea, he had the idea to use the moon as a detector. Yeah? So these cylinders are comparatively small. That's the reason why the resonance frequency is so high. You would get a lower resonance frequency if you have a bigger body. And the idea was to use the moon as a detector. The moon, of course, would also be deformed by an incoming gravitational wave. So what he did was he convinced the NASA to send a gravimeter, an instrument which measures changes in the gravitational field, to the moon with the Apollo 17 mission. And unfortunately, the instrument didn't work well. Yeah, it failed. So he put such an instrument on the moon. It was, in essence, it was just a spring balance. Yeah? So if the moon now starts oscillating under the influence of a gravitational wave, then the spring balance would also become oscillating. And that was his idea of measuring gravitational waves of lower frequency. But as I said, the instrument didn't work. And he died in 2000, and everybody believes that he never managed to see a gravitational waves. There was a certain even after his death, there were certain attempts to follow up on this kind of research. I think the most ambitious, the most sophisticated resonant bar detector that was ever built was Auriga. This was in Italy, near Padova. It's a cylinder. Can you see this? Here comes a cylinder out of this container. It's about 3 meters long. And when it's in operation, it doesn't look out of the things. It's completely inside this tank. And the whole thing is cooled down almost to absolute zero, to millikelvins. Yeah, so this is operating at very low temperature. I don't remember what the acronym Auriga stands for, but the U stands for ultra cryogenic. Yeah, so it's at very low temperature it's operating. This took data, or it tried to took data, I should say, for a couple of years. It was decommissioned some time ago. So it's no longer in operation. I think this was the biggest and most ambitious resonant bar detector that was ever built. Here is a diagram of how the construction works. So inside this tank, which is cooled down to cryogenic temperatures, the bar is suspended in a way that it is isolated as far as possible from seismic noise. And what is actually measured is not the motion, the deformation of the whole bar, as Weber did with his quartz crystals, but rather it's the motion of a little mass, 1 kilogram or so, which is attached to one of the ends. So if the cylinder starts oscillating, if the resonance frequency is hit, then also this little mass would be set into motion. And what is actually read out is the motion of this little mass, which is called an electromechanical transducer. So that was the principle of this thing. I said already in this case the L was bigger than in the case of the Weber cylinders. It was about 3 meters. But it's no longer operational. As far as I know, there are only 2 resonant bar detectors at the moment in operation, and both of them are spherical. That's a new idea, where the obvious advantage is that then you could detect gravitational waves coming from anywhere. Yeah? The cylinder, you get a good signal only if the gravitational wave is friendly enough to hit it from the side. Yeah? If it comes from the other side, you wouldn't get a strong effect. So with these spherical things, the direction plays no role. Here you see a person, so you get a good idea about the size. So it's pretty small. I think that's 60 centimeters or so in diameter. So this picture shows the instrument which is called Mini Grail. This is in Leiden in the Netherlands, a famous low temperature institute, the Kamerlingh-Onnes Institute. And this is also to be operated at some millikelvins. So that's not the way in which you operate it. Yeah? You put it into a cryogenic tank, and then the measurements are taken. And there's a similar, the same size, same principle, a similar instrument in Brazil. This is called Mario Schoenberg. It's named after a famous Brazilian theoretical physicist. And the 2 things are supposed to operate in parallel, so that one can do coincidence measurements. As far as I know, these are the only resonant detectors which are in operation right now. And you see they're fairly small. Yeah? So actually there's not much hope that you can see a signal with them. It's more like prototypes for maybe future instruments which are of a bigger size. So I told about this spectral density. Let me show you a picture of the spectral density for Mini Grail. So you see here frequency. You see here the strain sensitivity in this funny unit, hertz to the power minus 1/2. Yeah? And what was measured, this is not quite recent, this is from 2005. What was measured in one of the runs is this thick and somewhat oscillating curve. So if a signal comes, see the units, yeah? So this is 10 to the minus 22, 10 to the minus 21, 10 to the minus 20. So in order to see something, you have to be above this noise curve. So if during this run you wanted to see a real signal, it should have at least 10 to the minus 19 hertz to the minus 1/2. Which of course is a very strong signal which you don't really expect from gravitational waves. You expect them you really expect them more in this range here than up there. So Mini Grail is supposed to operate, to become improved, or maybe it has already been improved, so that you can observe actually down to 10 to the minus 21 in this unit, but you see only at very particular frequencies. Because of the shape of this thing, you have now 2 resonance frequencies. They are at about 3 kilohertz. Yeah? Very high frequencies for gravitational wave signals. And if you do not hit exactly one of the 2 resonance frequencies, then there's little hope that you see anything. So yeah, these things, these resonant detectors, they have become a little bit old-fashioned now. Since the gravitational wave signal has been detected with LIGO, everybody is talking about these interferometric detectors now. And most people think that that time is just going over these resonant bar detectors. I'm not quite sure. They could be useful for detecting some burst sources. And maybe they will come up in the future at some time again. In any case, I think it's instructive to study the principal idea of how they work, because you get some ideas about how a gravitational wave in principle could be detected. And that's why I've repeated this here. But of course, the real thing at the moment, everybody believes it's interferometric detectors. So let me now come to them. Oops. Sure.
So why did this idea with using the moon as a detector fail?
The instrument failed, not the idea.
Okay, well,
The instrument was sent to the moon. It was on board Apollo 17. I remember this very well.
okay,
This,
I see, but why didn't they try again?
there was no follow-up mission to the moon. Apollo 17, I think, was the last mission, right? Is it true? Or was it maybe 18, but not more than that?
When was it?
Early 70s.
Okay.
So the landing on the moon was 69. I remember this very well, one of the most exciting moments in my lifetime. I was 13 years old. I remember every minute of this night. It was during the night here in Germany when they stepped out of the lander. I remember this very well. Also, I followed all the later Apollo missions very closely. And I think Apollo 17 was 72 or so.
Okay.
And since then, we haven't sent, the US haven't sent anything to the moon. There are plans to start again a moon program, but they haven't yet.
But is it going to be more expensive than building like a new LIGO or whatever?
The question was if it's more expensive, like building something like a LIGO. Well, if you do a dedicated mission, yeah, if it's just the only goal to take such an instrument to the moon, then of course it's more expensive, yeah. But if you go to the moon anyway, and then taking this instrument with you, then this is not much more expensive than going without this thing. Yeah, these gravimeters, they are not very big, yeah, so they can easily be stored in a spaceship.
So it could be a realistic, let's say, detector for the
Yes. I'm not sure if there's anybody around who is pushing this now. Joe Weber is no longer with us. He was the driving force behind all this. I have no idea if anybody is eager to doing this, but it could be. If the NASA starts again a moon mission, then it could be that they will come. So I'm not absolutely sure that these resonant bar detectors are dead forever. It may be that they come up again. Okay, you were able to switch this off last time. Could we try to do this again? Okay, thank you very much. Okay, then I continue now with the interferometric detectors. I should have said the reason why Weber could convince the NASA to send this thing to the moon was not that, or at least not alone, that NASA was eager to measure gravitational waves. These gravimeters can be used also for other things. You have just for measuring seismic activity on the moon. And this was something which the NASA found interesting. And if it would have been detected gravitational waves, all the better. Yeah, but actually the reason, I think, why the NASA agreed to do this experiment was that they wanted to measure just seismic activities on the moon. Okay, let me check how much time do I have. 15 minutes, okay. Done this. Okay, should be section 4.2. Interferometric gravitational wave detectors. So these are in principle just Michelson interferometers. I think everybody knows what a Michelson interferometer is. Just to remind you, you have two mirrors and a beam splitter here. And the distances should be should be more or less the same. So a laser beam is coming in, it's split here. Then one is reflected here, goes back, and then this way, and the other one goes to this mirror and then back. And here it's a screen where the signal is measured. And what you get here is a superposition of the two beams. So you get an interference pattern. And the interference pattern changes whenever the distance between one of the mirror or both of them with respect to the beam splitter changes. So how do you measure gravitational waves with such a thing? The idea is that these mirrors, that they are suspended in a way that they are free to move in the horizontal direction, in the plane of the board. Yeah? So, of course, they cannot be freely falling in the strict sense, then they would smash to the ground. Yeah? So you have to suspend them. But you can have them more or less freely moving, as free as possible in the horizontal direction. So this is very tricky. When you realize this, it's one of the most important technical challenge to have these things moving as freely as possible in the horizontal direction. So the suspension is a very subtle aspect of this. If this is the case, now assume that a gravitational wave does us a favor to come in from this direction. Say a plus wave, where a plus mode, where this and this are the eigendirections. Then you would have a change of distance. This distance would become bigger, this smaller, and then half a phase later, this distance would become smaller and this would become bigger. And this would be visible as a change in the interference pattern. That's the basic idea. We will calculate in a minute what kind of phase shift is produced by a gravitational field, by a gravitational wave, and you will see that actually the amplitudes which can be measured in this way, they could be surprisingly small. This basic idea is very old. It's almost as old as Weber's idea of using resonant bar detectors. So the first idea, let's do a little bit of history. The first idea was by two Russian Well, Pavel always tells me I shouldn't call all citizens of the Soviet Union Russian, but I'm used to this. Yeah. So actually, I don't know what exactly are the national. Yes, Soviet scientists. So I would say Gerzenstein. This is probably a German Jewish name, I would guess. Yeah, and the other name is Pustervoit. And they suggested this in 1963. So you know that this type of detector now was able to measure gravitational waves, the LIGO detectors. They did this 1.5 years ago. And now many people discuss and there are controversial ideas about who should be awarded the Nobel Prize for this. In all these discussions, I've never heard the names of Gerzenstein and Pustervoit. Actually, in my view, they would be very natural candidates because they were really the first who suggested the idea, the principle of how this should work. And the paper is very well written. It is not just a rough idea of how shit could work. It's a very detailed analysis of how type of gravitational wave sources could be observed with this kind of detectors. So it's a very good paper, and I think they really deserve to be more. To stronger advertised as it is usually done.
Is it still alive?
I think so, yes. I asked Oleg, he says yes, yeah. Okay, so this was in '63, but for a couple of years nothing happened. In particular in the Soviet Union, they did not build such a detector. They never built a big detector. Yeah? There was a group in the Soviet Union and then later in Russia working on gravitational wave, a very strong group, headed by Vladimir Braginsky, who passed away last year or 2 years ago. But they never built a big detector, a competitive detector. Probably on the agenda in the Soviet times, they had other things which were considered more important than detecting gravitational waves. So as far as building a big detector, the Soviet Union and later Russia played no important role. So, so suggestions for realization was later. This was in parallel done, actually in Germany. And the leading figure was Heinz Billing from the Max Planck Institute in Munich, in Garching. He passed away a few weeks ago at the age of 102. So he's also out as far as the Nobel Prize is concerned. Yeah? Probably he wouldn't be considered anyway, but he was the driving force in Germany at the beginning. So he suggested this. He was, so to speak, the founding father of what later became GEO 600. And he was at the beginning of this development, and then later Carsten Danzmann played the leading role. I think some of you know him. He was here in the colloquium a little bit more, half a year or so ago. So he is now one of the Max Planck directors in Hanover. So he is, if one says that GEO 600 has two fathers, then he is the younger of the two fathers. Actually, it was originally planned to be built near Munich. So I remember in the 1970s when this development started, then the pictures, the simulations which showed the detector, they always had the Alps in the background. Yeah? So the idea was to place the detector in near the Alps, but then they found out that I guess the main reason was that the seismic background is more appropriate here in the north. So they built this near Hanover, as you all know. So GEO 600 was built near Hanover. So this was a long development, began in the 70s, and actually GEO 600 went operational, I think, around 2000. It was at the time when I was in Goem, yeah. So it must definitely be between 1999 and 2003. So I think it was around 2000. And in the US, there were 3 founding fathers. One was Rainer Weiss, German-born, but since his early childhood, citizen of the United States. He's an experimental physicist, also an important science manager. Then there was Ron Drever, experimental physicist, Scotsman, and the theorist in the game was Kip Thorne. Yeah, you know this name, I think, Kip Thorne. He was a scientific advisor for the movie Interstellar. Yeah, maybe that's.
Great achievement.
Yeah, that's. I think I'm not saying that it was the biggest thing he did in his life, but it's certainly what made him best known to the general public. So these 3 gentlemen were the initiator of the LIGO detectors. There's one in Louisiana is the one. Louisiana and Washington State. So these are 2 detectors actually. And the 3 in the beginning, they were the 3 directors of this instrument. So they formed something, well, how do you pronounce this in English? In Latin you call this a triumvirate, right? So 3 people. So there was a triumvirate in Rome, in ancient Rome. This one didn't go quite as bad as the one in Rome. Yeah? In Rome, some of them ended up beheaded, but it was not quite as bad with these 3. But there were also big quarrels between these 3. And after a couple of years, the funding agencies said this doesn't work in this way. We should have 1 director. And from that time onward, LIGO always had only 1 director. But in the beginning, it was this triumvirate. Rainer Weiss and Kip Thorne are still alive. Ron Drever, unfortunately, also passed away recently. He was demoned since a while, so it's not clear if he really understood that gravitational waves have been detected. So at this time, he was already in a hospital. But Weiss and Thorne, they are quite fit. And if I should bet who is getting the Nobel Prize for the detection of gravitational waves, then Weiss and Thorne are the most natural candidates. And the question is, who is the third? Could be a German, maybe. Let's see. It's not totally out of the question. So this was a development which started in the 1970s. As always, the main problem was to get funding, and this was closely coordinated. So Billing and Weiss were always in close contact. So they did. So Billing, of course, did it. He approached here in Germany the DFG, Deutsche Forschungsgemeinschaft, and Weiss approached what is this called, NSF in the USA. But this was always closely coordinated, and it was from the very beginning. It was the idea that these detectors should work together, so that they share the data and that everything should be done in close collaboration. And then also Italy and Japan entered the game. So this was a bit later in Japan. In Japan, there was a small detector, TAMA, which is no longer in operation, and they are now planning building a bigger one, a cryogenic one, also operating at low temperature. This will be called CAGRA. And there's another one in Italy. This is Virgo, which is also closely collaborating with these things. And LIGO, also there will be a third LIGO detector, which will be situated in India. So this is now in the planning stage. Was originally planned to have it in Australia, but the Australian government was stupid enough not to give the money. Probably now they are not happy about their decision. It was made before the gravitational waves were detected, and then India got the India made a proposal, and so the third LIGO detector is now being built in India. So that's the situation. What we have on Earth for the detectors. I will show you pictures and tell you a little bit more, in particular about the two LIGO detectors, which are the ones which found the gravitational wave signal in 2015. Has anybody been to Geo 600 in Hanover? Yeah, Pavel has been. Chris also, yes. It's also something which is not so very impressive, right? So it's a low budget. It's a low budget instrument. It's comparatively slow, but small, much smaller than LIGO. And the idea was from the very beginning just to test technologies. So the people in Hanover, they are not so much disappointed that they never saw a gravitational wave signal. Actually, they didn't really expect this. The idea of Geo 600 was just to test technology. And in this respect, Geo 600 was extremely successful. So in particular, the laser technology, which was built for LIGO and will be then implemented into LIGO, was to a very large extent developed in Hanover. So this team was, in this sense, very successful. But they worked on a low budget, and it's really not very impressive. So it's, they built it in a place which belonged to the university, actually to the Institute for, how do you translate this? For Obstanbau. How do you say this in English? Yeah? So fruit growing. Yeah? So there are fruit trees around the place. You can still see them. And the architecture was really carried out on a very low budget. So it looks a little bit like the huts where a local farmer is storing his instruments. But if you go inside, if you see the laser, of course, this is then very impressive. Yeah, but from the outside, it's not very impressive. I've never been to LIGO. People who have been there tell me that LIGO is much more impressive. So this is really a big site and very sophisticated. Okay, I think time is more or less out. So on Friday, I will then, oops, what is it? Yes, I'm already over time. So on Friday, I will then discuss what a gravitational wave is doing to such a thing. So we will derive a formula for the phase shift in terms of the incoming gravitational waves. And then we will discuss also the sensitivity diagrams for these gravitational wave detectors. Okay, see you on Friday.